Hello, ladies and gentlemen. Root Gear here, wishing you all well as we take a look at question B2 on our 2017 intermediate paper. So the symbol n with an exclamation mark is pronounced n factorial. Oh, they even say that down here. Okay. And it represents the product of the positive integers from 1 to n. So here's a nice little expression for it. N factorial is n times n minus 1 times n minus 2 times n minus 3 times, all the way down to times 4 times 3 times 2 times 1. Okay? So for example, 4 factorial has a value of 24 because 4 times 3 times 2 times 1, you just count down, you multiply them all out, is 24. Okay, so we've got 4 parts here. A part, determine the value of 7 factorial over 5 factorial. So we want to actually work it out. Okay. So we could just say, okay, well, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. And then, oh, look, we've got factors of 5, 4, 3, 2, and 1 here. And we've got another copy of 5 factorial up here, so they just cancel out. We're left with 7 times 6, or 42. So 7 factorial over 5 factorial is 42. And that's all we need for that one. Okay, B. Determine the positive integer n for which 98 factorial times 9,900 is n factorial. Okay. How do we approach this one? Well, n factorial has to sort of look like this, doesn't it? N times n minus 1 times n minus 2 and so on. Now, it's 98 factorial times something else. Okay. Now, if we were to take 98 factorial and multiply on 99, because 98 factorial is 1 times 2 times 3 all the way up to 98, if you multiply by another 99, you should get 99 factorial. Okay? And if you multiply 99 factorial by the next number, 100, you'll get 100 factorial. If you multiply that by 101, you'll get 101 factorial, and so on. But why am I pointing this out? Well, 99 and 100, we get, what did we have here? We had 98 factorial times 9900. 9,900 is 99 times 100. So if we just go ahead and split this up into 99 times 100, then this part here turns into 99 factorial. This part here turns into 100 factorial. So n would have to be 100, and there we go. Okay. A nice little value of 100 there. And we're sort of just getting comfortable. We're exploring these factorials. Now C, determine the positive integer m for which m plus 2 factorial divided by m factorial is 40,200. And what can we do here? How can we divide factorials? We did it here. Okay? And so what we might be able to sort of do is say, okay, m plus 2 factorial on top, m factorial on the bottom. M plus 2 factorial will do m plus 2 times m plus 2 minus 1, which is really m plus 1, times m minus 1, and just keep going down, times 2 times 1. But on the bottom, m factorial is m times m minus 1 times m minus 2, all the way down to times 2 times 1. And so just like with 7 and 5, we can see, oh, there's an m factorial on the bottom, but there's an m factorial on top, and those can cancel out. So we get a very nice, simple expression here. M plus 2 factorial over m is really just m plus 2 times m plus 1. And we can expand that out. That's m squared plus 3m plus 2. And what value is this supposed to be equal to? 40,200. And that's what we're looking at, 40,200. Off the top of my head, I can't. I think it's 200 and 201. I think I'm just looking for two consecutive numbers that multiply this way. You know, if we have trouble finding them, we can just subtract 40,200 from both sides, but this is going to be a little annoying to try and factor, although, you know, if we need to, we can use the quadratic formula. But what would we have? We'd have 40,198 equals 0, and so you could quadratic formula that. But I think you can get m minus 200. No, 200 wouldn't work. 199. And then m plus 202. Those two differ by 3, and the 2 and the 9 give me an 8 there. So yeah, that should work. And again, quadratic formula, you can prove it. So either m is negative 202, which is not going to work because we've got to have positive integers, and we specifically were told positive integer m, so we must have m is 199. Okay, that's C part all done with. So we really just have the D part left to go. D, suppose that Q is a positive integer and R is the number for which Q plus 1 factorial minus Q plus 2 factorial minus Q plus 1 factorial is Q factorial times R. Show that for every positive integer Q, R is a perfect square. Okay. So we've already seen a couple times how we can sort of break off little bits from our definition. So Q plus 1 factorial is Q plus 2 factorial. Q plus 2 factorial is Q plus 2 times Q plus 1 times Q all the way down to 1. But this here is the product of all the numbers from 1 to Q, so this is really Q factorial. Just like this part here is Q plus 1 factorial. But the reason I'm going to break it down into Q factorial is because in the expression they've given me, we've got a Q factorial sitting out here. So we can write Q plus 2 factorial and Q plus 1 factorial as just expressions of Q times Q factorial. Q plus 2 factorial minus Q plus 1 factorial is Q plus 2 times Q plus 1 times Q factorial minus Q plus 1 times Q factorial. So we can take out the factor of Q factorial. Okay. And then we'll have Q plus 1. Actually, we can take out a factor of Q plus 1 as well. So we're left with Q plus 2 and then minus 1 here. So we've got Q factorial, Q plus 1, and then another Q plus 1. Okay. So R times Q factorial, which by definition of what R is this difference. But we just showed that that's going to be Q plus 1 squared times Q factorial. So we conclude that R is always going to be Q plus 1 squared. So R is always a perfect square, which is exactly what we wanted to show. And there we go. There wasn't anything else we needed to do here. We just need to show R as an integer, which is a perfect square. And there we go. We, in fact, know what R is going to be in terms of Q, but they didn't ask us for anything like that. Okay, so that's question number 2 all dealt with. Up next, we're going to finish off the contest with question B3. Give it a try before joining me, and I'll see you for that next time.